So reading the problem, we see some courses may have prerequisites. For example, to take course 0, you have to first take course 1, which is expressed as a pair 0, 1. So 0, 1, and it says to take course 0, you have to take course 1. So basically, once you do course 1, you get to course 0. We can kind of represent it like this. And if we use kind of this representation of like taking a class and then, providing an arrow in between that class and the next class, I think we can make this problem a little bit easier. So just keep that in mind. Now, given the total number of courses and a list of prerequisite pairs, is it possible for you to finish all courses? All right, well, let's see. In the first example, we're given the num course is courses 2, and we're given prerequisites. Prerequisites are 1, 0, and that's it. 1, 0. Okay, so basically, to get to course 1, you have to finish course 0. So 0 will give us course 1. We see that there are a total of 2 courses to take, and once you finish course 0, you can take course 1. We're told that this is possible. This is a valid. This is a valid course schedule. So let's put that right here. This is valid. Okay, that's cool. Let's look at the next example. Next example, num courses is 2 again. So num, let me just draw a little line in between these. Num courses is 2. The prereqs will be, it looks like 1, 0 and 0, 1. So 1, 0, 0, 1. So let's kind of draw this out now. To take course 1, you have to take 0, which is represented right here. To take course 1, you have to take course 0. So 0 leads to 1. But now looking at this example, to take course 0, you have to take course 1. So in other words, to take course 0, you have to take course 1. But do you see how this is kind of confusing right here? Like, look at this. To take course 0, you have to take course 1, but to take course 1, you have to take course 0, but to take course 0, you have to take course 1, take course 1, you have to take course 0, and we actually end up in this weird cycle state, right? Where to take course 1, you have to take course 0, and to take course 0, you have to take course 1. It just kind of keeps going on and on. So we see that this is, and we're also told that this is invalid. This is invalid course schedule, right? So we see and realize that this cycle that's created, in using these prerequisite courses, this cycle is the reason that this is invalid. And it also just doesn't make sense to us, right? So, at this point, hopefully you realize that we can kind of represent this as a graph, right? Using this idea of like taking one class to take the next class, we can just make each class a node, right? In other words, make 0 its own node here, make 1 its own node, and each arrow in between will represent like the prerequisite before. So to take course 1, an arrow will come from 0 to 1, meaning that 0 will be the prerequisite of 1. Okay, so we figured out that we need to use a graph. Now, using this graph, we need to somehow figure out if there's a cycle anywhere in our graph, because here we see cycle is there, and that's the reason it's invalid. So how can we figure out if there's a cycle? Well, one way I feel like we could do this is like, we know that we need to look through all the nodes somehow. And one way we can do this is by doing a, let me get another color, DFS, a depth first search, right? We'll recurse through all nodes. And here in our example right here with the cycle, we see that 0 goes to 1 and 1 goes back to 0. So basically we see that 0 has been seen already, right? So if there was a way where we can keep track of the nodes we've visited already, then we can kind of check to see if there's a cycle, basically. If a node has been visited already, then we kind of know that there's a cycle. So we need to somehow find, so let's say we perform a DFS here. We'll pick any node to start with, and we'll just recurse and explore through all of its neighbors. If it hasn't been visited, right? Because if it has been visited, then we know that we have a cycle. But if it hasn't been visited, we'll go and explore that node. So for example, let's say we start here at node 0. Let's visit node 0, and let's explore all of its neighbors. So we see that 1 is the only neighbor here. So let's do a preliminary check. Has 1 been visited already? Well, I don't see a V that's going to indicate that is visited. So no, it hasn't been visited. So let's go ahead and visit that. So now we're going to go here and visit it. Now we're going to explore all the neighbors of 1. And we see that 0 is the only neighbor of 1. Has 0 been visited? Well, yes, we've given it this tick right here, so it has been visited already. And since it's been visited, there's a cycle, basically. So that's kind of the intuition kind of going behind how we're going to solve this problem. Now, before we start coding, let's run this idea through a few examples, right? So here, let me start a new page. And let me, off the top of my head, I think one quick example that I can use is, let's use with 3 classes, num course 3, and prerequisites will be 3, 2, 2, 1, 1, 0. So this is just like really quick and easy. We see that we need to do 0 to do 1, then 1 to do 2, and 2 to do 3. Right? In other words, if we were to represent this as a graph, we'll do 0 to do 1, 1 to do 2, 2 to do 3. Okay? Now let's just kind of run our idea of here. This DFS recurs through all the nodes. Check to see if visited. If in visited. All right. So it's a very basic idea, and maybe as I explained, it'll make some more sense. So let's start here, and let's just start with node 0. So is 0, and we'll have a visited set right here. My bad. Is 0 in the visited set? Well, no, I don't see 0 here. So let's visit this. We'll add it to our visited set, and let's explore all of its neighbors. How many neighbors does it have? It has number 1. So let's check to see if 1 is in our visited set. I don't see 1 in our visited set here. So let's go ahead and visit it, add to our visited set. Okay, now let's check the neighbors of 1. Okay, so 1 has the neighbor 2. Is 2 in our visited set? Once again, I don't see 2 here. So let's go ahead and visit it. We'll add it to our visited set. And finally, we see that 2 has the neighbor 3. Let's check to see if 3 is in our visited set. In our case, 3 is not in our visited set. So let's go ahead and explore it, add 3 to our visited set. And we see here that there's no cycle. Once we've recursed through all the nodes and check to see if anything is not in our visited set, once it's past all those 2 cases, we see that there's no cycle here. So this is a valid course. Okay, cool. Now let's try one more example here. Okay, so this is an example of one that is valid. Let's add just one more edge to make this an invalid one, where we'll add edge 0, 3, where to do 3, after you do 3, you go to 0. So basically, this will look like this. Okay, so let's just run through this example one more time now. And here we go. Let's start here. So let's start with any node. And this time, just to show that we can start with any node and get to the same answer, we'll just start with node 2. So 2, is it in our visited set? I don't see it. So let's go ahead and visit it, add it to our visited set. Okay, let's explore all the neighbors of 2. Well, 2 has the neighbor 3. Is 3 in our visited set? No. Let's visit 3 and add it to our visited set. Now let's explore all the neighbors of 3. We see 0 is a neighbor of 3. Is 0 in our visited set? No. Perfect. Let's visit it and add 0 to our visited set. Now let's go check the neighbors of 0. We see that 1 is a neighbor of 0. Is 1 visited? Well, I don't see it in our visited set, so no, it's not visited. Let's go ahead and visit it and add it to our visited set. Perfect. Now, does 1 have any neighbors? Yes, we see that 2 is a neighbor of 1. Is 2 in our visited set? Yes, it is. 2 is in our visited set. Hence, We see 2 is there, hence there is a cycle in our graph. This is invalid since there's a cycle. Okay, now let's run this through one last test case. Okay, where we are going to be given num courses 3. We'll have 3, 2, 2, 1, 1, 0. So in other words, 0 will go to 1, 1 will go to 2, 2 will go to 3. Let's also add to 0. Or in other words, to take 2, you also have to do 0. Okay, so, basically, like, if we were looking at this like a normal schedule, like a normal course schedule, some classes you take, you don't need to take another prerequisite to take the end class, right? Like here, it's clear that we need to take 1 in order to take 2, but sometimes you don't need 1. You can just go straight to 2 if you're like really good, or I don't know, you can you can just skip a class or something. But let's just go through this example with our visited set explanation. We'll just kind of see if this will work for this test case, right? I think it's important to keep in mind some test cases while you're going through your code and building intuition. So let's do this. Let's start with node 0. Okay, let's just run through our example like we did in the last one here. So is 0 in our visited set? No. Let's go ahead, add it to our visited set, and let's explore the neighbors of 0. For the sake of staying chronological, I'll just go to node 1 instead of node 2, okay? So now let's go explore the neighbors of 0. We see that 1 is a neighbor of 0. Is 1 in our visited set? No. Let's visit that one. Let's add it to our visited set. Okay, let's check what are the neighbors of 1. We see that 2 is a neighbor of 1. Let's go ahead, and we see that 2 is not in the visited set. So let's go ahead and visit it and add it to our visited set. Okay, so what are the neighbors of 2? We see that 3 is a neighbor of 2. Has 3 been visited? Well, I don't see it in our visited set, so let's go ahead, visit 3, add it to our visited set. Now, at this point, does 3 have any more neighbors? No? Okay, so at this point, I hope you see that the recursion looks something like, so 0 will go to 1, 1 will go to 2, 2 will go to 3. And now that 3 has no more neighbors, we are going to go backwards, right? In the recursive stack, we're going to go backwards since there's no more neighbors. Does 2 have any more neighbors? No. Let's go backwards to 1. Now, does 1 have any more neighbors? No. So we're going to go back to 0. Does 0 have any more neighbors? Yes. So let's go ahead and explore that. So we see that 2 is a neighbor. So we're going to go see 2. Or actually, before we even do that, so we're back to 0. And 0, does 0 have any more neighbors? Well, we see that 2 is a neighbor. But look at this. 2 is in our visited set. So that means since 2 is in our visited set, there's a cycle, right? If we go to a node that is in our visited set already, if we explore a node that's already in our visited set, we know that there's a cycle. But just look at this graph really quickly. Like, let's just forget everything, forget all, let's just look at this. I'm gonna change my colors really quick. Forget all of this, forget all of this, forget everything. Look at our graph. Do we see any cycle here? Okay, so let's see. Can I get to 0? If I start from 0, can I get back to 0 using any path? Well, nope, I can't. Starting with 1, can I get back to 1 using any path? No, I can't. Starting with 2, can I? No. And 3 is its own no, it's a no, nothing. So I can't, there's no cycles here. But according to like our code, our intuition so far, as long as we've seen it in our visited set, it looks like this one will produce an invalid course schedule when it's actually valid. So maybe we can account for something else. There's one thing that we can account for, okay? So if we look back at our original few examples, right? Let's look at this idea of exploring and being completely explored. So what does it mean to explore? Exploring means that we have other neighbors to go to. So exploring equals more neighbors. Okay? But explored, meaning we're done exploring, right? No more to be, there's no more neighbors to explore. Explored means we are done exploring. Hence, no neighbors, no more neighbors, rather. Okay, so let's just kind of keep this idea in mind of exploring, explored, all this, okay? So let's run our example with this, or let's run some intuition with this example. Let's visit 0. Okay, so we'll see that 1 is a neighbor of 0. Is 1 in the visited set? Well, here, let's also make a visited set. 0. Is 1 in the visited set? No, 1. Okay, so now we're recursing to 1, adding to the visited set. Now, do we see 1? Is there any more neighbors? No. So we can say that 1, since there are no neighbors, we can say that 1 is completely explored. So let's just mark it as explored. Now we're going to go back to 0. Does 0 have any more neighbors to explore? No. So we can mark it also as explored. So I think let's kind of go off this idea of exploring. Let's go through another example. Let's go through this next example here. Let me erase this example. We know that there's a cycle here. We see it, right? So let's just go through this example one more time with this new visited and explored idea. 0. We'll go to 1. We'll go back to 0, okay? So, and let's have a visited set. Or let's just mark, we don't even need to keep a set. We'll just mark it on our graph. So let's try this example. So is 0 visited? No. Okay, let's start with 0. And let's explore all the neighbors of 0. We see that 1 is a neighbor of 0. Is 1 visited? No. Let's go ahead and recurse to 1 and visit it. Okay, now 1 is visited. Let's go check all the neighbors of 1. We'll explore all the neighbors of 1. We see that 0 is a neighbor of 1. But oh wait, 0 is visited. 0 isn't explored though, right? Here, 0 and 1 were explored, so we were fine. Here, 0 isn't explored, but it's visited. So maybe, since it's visited but not explored, maybe that could be our requirements to make this invalid. All right. So here in our example number 1, we saw that each thing was visited, each node was visited and explored, and because each node was able to be visited and explored without any cycles, without seeing a previous visited node. So maybe the intuition should be, if a node is visited and not explored, then there's a cycle. If a node is in the visited set and not in an explored set, which we'll also have to make, then there's a cycle. So let's try this with the next example. Let's try this with this example. Our last example here. Let's keep a visited set. Let's keep an explored set as well. Okay? And I think once we go through this example, you will see exactly what I'm talking about. Okay, almost done here. So let's go ahead. Let's do this. So we're going to have a visited set. We're going to have an explored set now. Okay? Okay, so let's start with node 0. So 0, is it in our visited set? No. Let's go ahead and add it to our visited set. 0. Now let's check. Does 0 have any neighbors? Yes, it has 2. But let's just go to neighbor number 1 first. All right. Is 1 in our visited set? No. Let's recurse to 1. Add it to our visited set. Perfect. Does 1 have any neighbors? Yes, it has neighbor 2. Is 2 in our visited set? No. Let's recurse to it and add it to our visited set. Okay. Now, does 2 have any neighbors? Yes, it has neighbor 3. So is 3 in our visited set? No. Let's recurse to neighbor 3, add it to our visited set. Does 3 have any neighbors? No. No more neighbors. And remember, at the very top here, we said exploring means there's more neighbors, Explored, which means we're done exploring. If a node is explored, completely explored, that means there are no neighbors left. So in our case, 3 has no neighbors left, meaning that it's completely explored. So since there are no neighbors left, let's add 3 to our explored set. 3. And we'll recurse back to 2 here. Okay, does 2 have any more neighbors left? No. Since 2 has no neighbors left, we'll add this to our explored set. We'll recurse back, or we'll go back to 1. Does 1 have any more neighbors left? No, no more neighbors. Let's add this to our explored set, 1, and we'll finally go back to the 0 node. Now, does 0 have any more neighbors? Yes. Now, let's look at this. We'll check this last node. Is 2 in our visited set? Well, yes, it is, in fact. We see that 2 is right here. And let's also make a check. Is 2 in our explored set? Yes, it is. If it's in both sets, that means there's no cycle, as we've shown before, right? Since it's in both sets, if it's in the visited, let's just make it one more check to see if it's in the explored. Since it is, there's no cycle. So all we're going to do is not recurse to 2 at all. And we'll finally mark 0 in the explored set. And hence, since we've been able to visit and explore all the nodes with no problem, then we know that there's no cycle, and hence this is a valid schedule. Okay, schedule. So this is the intuition behind it. Let's get into the code. All right, so let's look at this problem. How can we use our inputs, num courses and prerequisites to create a graph? Well, we see that prerequisites, looking at these examples, prerequisites contains the edges between the nodes. It also contains like the node values, but it's going to be kind of hard, kind of inefficient to iterate through the prerequisites just to find like the nodes, like just the initial nodes. Like I think we can use prerequisites just for the edges, but is there any way where we can find the nodes without the edges? Well, we have this other, input num courses. If we just iterate from 0 up to num courses and exclude num courses value, then we basically have all our nodes. For instance, here num courses is 2, prerequisites is 1 and 0. So if we just go iterate from 0 up to 1, we have all our nodes. If num courses was 3, we'd iterate from 0, 1, 2. 0, 1, and 2 would be our nodes. So let's do that. Let's just iterate through num courses and use prerequisites to create our actual graph. So let me make another helper method, and I'll just call it build graph, okay? So what is the form that we want our graph to be in? We know that it needs to be in some type of adjacency list structure. I think one way that I personally like building my graphs is by putting them in the form of a hash map or a map where the keys will be integer in this case, since each node is a number course, and num course is an integer, and the value here will be a list. The value of list of integers, and the value will be basically the neighbors of each of our courses. Okay, so let's go ahead and build this idea. So let's make another helper function, public map integer list integer, and we'll call this build graph, okay? And this is going to take the inputs of can finish, and you'll see why in a second. Okay, so we have these. Now, we're going to create an actual map. This is going to be what we return. Integer graph equals new hash map. Gosh, sorry for all these typos, guys. And we'll go ahead and return graph when we're done. Okay, so let's first initialize our graph with just the nodes. Let's not think about the neighbors just yet. Let's just go through and put all the nodes into our graph. So how can we do this? Well, let's just iterate up to num courses, right? Or we'll just go through all, we'll just iterate up to num courses and put these values into graph. So for int I equals 0, I is less than num courses, I plus plus. So since we're trying to exclude num courses value, we're just gonna iterate, that's why we have this less than here, we're gonna iterate up to num courses, excluding that value. And let's put I in a new array list. All right, we're just initializing it, making sure that there's not gonna be any null values for our nodes. There's always gonna be an empty array list for every single one of these, okay? And after we do that, let's go ahead and populate the neighbors for each of the nodes. Now, we know the neighbors, or we know the edges with this prerequisites. So anytime we see an edge from one node to the next, let's just add that neighbor from using that edge to the graph. Okay, so basically, let me do a quick example here. So let's say we had 1, 0. We're just going to use example 1 in this problem, right? So in our hash map, we would have had here, this right here. Sorry about that. 0 and 1. See, everything's going to be initialized. Now, we know that to take course 1, we have to take 0. Or in other words, 0 is going to lead to 1. Okay? So we see that there's going to be one edge from 0 to 1. Or in other words, in this hash map, we'll have the neighbor of 0 be equal to 1. An array list with 1 in there. Okay? Let's say we had 1, 0, and 0, 1. Now we see that the second value is going to be is going to look something like 1 will lead to 0. So in the actual hash map, we'll go to key 1 and we'll add a 0 into the array list into its current array list, where the array list will represent the neighbor. So hopefully that made a little bit of sense. Let's go ahead. I think maybe when we actually build this out a little bit more, it'll be a little bit more clear. But let's iterate through our prerequisites for int, and let's just take the arrays, and we'll say int edge in prerequisites. Hopefully I spelled that right. And now we know that the prereq, the actual class you need to take before, is going to be in the first index, right? Here, to take class 1, you need to take class 0. So it's going to be in the 1 index of our edge. Okay, so it's going to be edge 1. And then the class you take after, int class after, is going to be edge 0. Okay, so now all I'm going to do is get the neighbors of my prerequisite class. So how do we do that? Well, let's get the neighbors of our prerequisite class. So we do list integer if I can spell, neighbors equals graph.get prereq. Okay? And all we're going to do is add the class that we need to take after to our neighbors. We're going to make class after a neighbor of our prereq. So let's do neighbors.add class after. And finally, let's update our graph. How can we do this? Well, we'll just put this back into our graph. So graph.put prereq neighbors. And after we iterate through all of our prereqs, we should have a fully updated graph with all of our nodes and all of its neighbors. Okay, so we built our graph. Nice. Let me go ahead and delete some of this stuff. Okay, great. So here, all this was so we can put this up here as our first line. List integer graph equals build graph num courses and prerequisites. All right, here we go. Perfect. Hopefully I spelled all of these right, man. Really hope I did. Okay, so now we know we have our graph. Now, remember, the intuition behind the problem was to create a visited set and an explored set. And basically, if a node that we were visiting or where we were exploring was in the visited set and it was not in the explored set, that means we have a cycle. Now, if it was in the visited set and in the explored set, then we're fine. We're okay. Let's just keep iterating through, check to see if there's any more cycles. So let's go ahead and create two sets, one representing the visited set and one representing the explored set. Okay, integer visited equals new hash set, and one more representing, oops, my bad, the explored set. And we have this. Okay. Okay, so now that we have our graph, we have a visited set, we have an explored set ready to be used. Let's actually recurse through all our nodes. So I said we had to use a DFS to recurse through all our nodes to check if there's a cycle. So let's go ahead and run some form of DFS. So let me make one more DFS function. And we'll say public. And what would our return type be? Well, one easy cycle detection implementation is to return a Boolean, where this Boolean, if it's true, that means there's a cycle in our graph. If it's false, there's going to be no cycle in our graph, okay? So just keep that in mind. And hopefully as I keep coding this out, you'll see this, code out pretty nice. So the parameters will be, it's going to be a node. We're going to pass in our visited set. We're going to pass in our explored set and our graph. So let me just pass in all of these things up here. So node, the visited set, the explored set, so visited set, and then explored set. And I think this is all we need for right now. So when we run through a DFS, the first thing we're going to want to do, we're only going to run DFS on the nodes that we haven't explored in the can finish. All right, you'll see this afterwards. But now, if we do run a DFS on all the nodes that we haven't explored, the first thing, or visited rather, the first thing we're going to want to do is visit it. How can we do that? Well, we'll just add it to our visited set. So the first thing we'll do, visited.add node. All right, perfect. Now we also need to run a DFS on all of its neighbors to check if there's a cycle within the neighbors. And once again, I'm going to make a comment. If this returns true, there is a cycle. Else, no cycle. Okay? So now we've added our visited set. Let's get the neighbors of this node. Okay, so how can we do that? Well, we have it in our graph, in our handy dandy graph. So let's go ahead and just grab all the neighbors. So we can do that by doing graph.get node. Okay, so we have all the neighbors of the node, and now all we're going to do is iterate through the neighbors, and we're actually going to run a DFS on all the neighbors. So how we'll do that is for integer neighbor in neighbors. Okay, now what are we going to check? If the node is not visited, let's go explore it. Okay, so if the visited set doesn't contain our neighbor, we are going to explore it somehow. Okay, we're going to recurse to it. Okay, so we're going to DFS here. Okay, and I'll come back to this in a second. Now, if the node is not in the visited set, if the node is in the visited set, we want to do one more check. We want to check if it is in the explored set. Now, if it is not in the explored set, what does that mean? That means it's only visited, not in the explored. That means there's a cycle. So, else if the explored doesn't contain the neighbor, what does that mean? There's a cycle, and we're going to return true. And remember, if this returns true, that means there's a cycle in our graph. Okay, we're going to return true. Now, and now finally, let's say we pass through this. We're iterating through all the nodes, and we iterate through all the neighbors, recurse through all the neighbors. After this, all we're going to do is add our current node to the explored set because we're done recursing through all of our nodes and all of our neighbors. So once we're done with all our neighbors, that means there's nothing more to explore. So hence, we're going to add our node to our explored set. And finally, if we add our node to our explored set successfully, that means there's no more cycle from that node. Okay, so we'll just return false, meaning there's no cycle. So now utilizing these booleans that we're returning, one last check we can do here in our visited condition. Let's just do this. This is an easier, this is only an easy way to like do the cycle implementation stuff. This is like a way that I usually use when I'm like going through trying to find a cycle. So if I'm returning a boolean, let's just do one last check. If DFS neighbor graph visited explored. So if this comes back as true, that means here we return false. Okay, I mean sorry. If this comes back as true, that means there's a cycle. So we return true. So does that make sense? Like if it all comes down to if our explored set doesn't contain the neighbor, because if this triggers a true, that means this will come back as true, and hence this will return true here. And if this returns true, that means we have to code out some implementation at the very top to say that it can't be finished. Okay, but just look at this, and keep in mind, true means that there's a cycle. Now, if this returns true, this will come back true here. If this returns false, meaning there's no cycle, this will come back as false here. So it's never going to it's never going to actually like trigger. So we're never even going to hit this statement. So that's how this kind of DFS will work out for us. Now let's actually code up the top. Oops. So let's code up the top. This is going to be very straightforward. We're just going to perform a very simple DFS on all of our nodes. So how we can do that is just do int I equals 0. I is less than num courses, I plus plus. And, oops, my bad. And all we're going to do is, we're only going to iterate through the nodes that aren't visited, right? So if visited does not contain I, then we'll perform a DFS. DFS I graph visited explored. Now remember though, this is going to return a boolean, right? This is going to return a boolean true if there's a cycle. So let's just put this in another if. So if this comes back as true, that means there's a cycle. This means that our problem can't be done. We cannot finish. There's a cycle in our graph, so we're going to return false here. Okay? Otherwise, if we iterate through the whole thing and we never trigger that statement, that means we have a valid path, we have a valid course schedule, so we'll return true here. And that is everything. Hopefully I typed everything correctly. Let's see, run it. Hopefully, okay, here we go. I knew there was going to be something. Let's see, can't find symbol, neighbors. Did I spell? Oh, that's why. I spelled neighbors wrong. There we go. Neighbors, okay, hopefully now this works. I knew it. Okay, so it's always something. Neighbors, probably spelled that wrong again. Yeah, my bad. All right, here we go. Third time. Dang it. Okay, so explore neighbor. Did I spell this wrong once again? I bet I did. Neighbor. Okay, let me spell this right. I'm really sorry, guys. So neighbor. Okay, hopefully now. Come on. Okay, pass the test case, pass the base case. So let's run, submit the whole thing. Hopefully this works for us. And it does. Awesome. This works. This is an easy cycle detection implementation. And let's just go to the runtime really quickly. So because we iterate through or recurse through all the nodes once and all the edges one time, and we only recurse through them once because we're constantly checking if it's in the visited set, constantly checking if it's in the explored set. So let's just go through the runtimes really quickly. So because we only because we only recurse through all the nodes and edges once, how do we know we're recursing through them once? Well, it's because we constantly keep adding to our visited set, adding to our explored set, and we're checking to see if it's in each of these before we actually recurse to that node. So because we only recurse through each node once, we recurse through all the edges once, the runtime for this will be O of E plus V, where V represents all the nodes and E represents all the edges. So we're just we're just recursing through everything one time. So yeah, guys, this is how you do the problem. I really hope this was helpful. Please let me know if you want me to do any other problems. And just let me know if there's anything I could do to improve. Let me know if there's something you didn't understand here or something that I could clarify later. I'm more than happy to do that. But yeah, hope you guys have a good day.